Okay, Matt and I are here to now try to summarize everything we've done this year and are going to do in the next 2 weeks. So this is Math 60 in a nutshell. Say hi, Matt.
Hello.
All right, here we go. We started the semester looking at linear functions, eh?
Mm-hmm.
So what is a linear function? Matt?
It's a line.
It's a function that is of the form mx plus b. Remember that formula way back in the day? And m represented the slope, and b represented what?
The y-intercept?
The y-intercept. And this got, and we all knew that this was looked like on a graph. The graph was a line. Woo! Boring. But nevertheless important in our studies here. And then we solved equations like 3x plus 2 is equal to 2 times parenthesis x minus 1. That was a linear equation, and we solved for this using what we called inverse operations. And we got the x's on one side, and we got the variables on one side. Well, instead of calling them x's, because they could be y's. Variables on one side and the constants on the other. Cool?
Totally cool.
Pretty basic, totally cool. Constants other side. Yeah, can anybody see what I'm writing here? And again, how do we identify it as a linear equation? We'll look at the exponents of the x's, and the x's are raised to the first powers. Beautiful, right, Matt?
Beautiful.
Nice. So, I think I'm good with linear functions.
I think so.
All right, very cool. Moving on. So then we moved on to quadratic functions, which look like what, Matt?
ax squared plus bx plus c.
Very good. He's earning his money, folks. Ax squared plus bx plus c. And so we identified these as quadratic because the highest power is 2. Well, I should have said highest power. Degree is highest power, but whatever. I'm on video.
Reasons and things.
So the highest power is 2. That's how we identify what it is. And we remembered that looked like, what does that look like when we graph it? It looks like a parabola, either happy or sad. And that all depends on whether the leading coefficient is positive or negative. And then we had some occasions where we might have had a quadratic equation, plus 5x plus 6. And when we had our quadratic equations, we'd always make sure that we first set them equal to 0 and then factored. I hope I factor this right while it's on the camera. I think I'm factoring it right. Is that right, Matt? And then we use the zero product property to say x is either equal to -3 in this case, or x is equal to -2. That was our end game with quadratic functions. So first being able to identify them, then being able to graph them, and then being able to solve their equations. Anything I'm missing, Matt?
How do we graph them?
How do we graph them? This is for, we find the vertex. Oh, good question, Matt. Good question. To graph, we need to know the vertex. Actually, how we did it. Oh, to graph. There we go. Graph. Good question. What we did is we found the zeros. And then, wait, he's laughing at me, so I'm going to pause. Okay, I'm back now. So to graph, we're going to graph the zeros, and then we take halfway through, we find the vertex. And then remember, you can also plug in for the input x. So plug in for x and come up with some outputs. But that was kind of our end game. Some parabolas don't have real zeros, so they're a little more difficult. But on my exam, they will have zeros. Okay. Real zeros. All right, moving on. Oh, another good point to make is that both the quadratic, actually, let me make it on the next slide. Hold on. Okay, this point that I'm trying to make is linear and quadratic functions are specific forms of a bigger group called specific forms of polynomial functions. And so polynomial functions we did in chapter 5 and chapter 5, that's 5. And basically they have, what would you call them? Non-negative integers, powers, non-negative integer powers. Yes? Would you go with that,
Yeah.
Matt? Or whole number powers.
Counting numbers.
Yeah, no, not counting, because it
and
could have an
zero.
x to the 0, which is the constant term. So those are specific forms of polynomial functions. And we multiplied, added, and subtracted and did a lot of stuff with polynomials. But now, moving on. So that leads us to the rational functions. A rational function is a function of the form p of x over q of x, where p and q are what we previously talked about, polynomial functions. So basically, if you take two polynomials and you divide them, you get a rational function. So how are you going to recognize these? You're going to recognize these as there is a variable in the denominator. So a more specific example Matt is going to give us is, go ahead, Matt.
X squared plus 5x plus 6.
X squared plus 5x plus 6, I've seen that somewhere, over,
X squared.
he's just going to say x minus 1. Very good, Matt. So this,
Boring.
this expression is a rational expression because you can see, I can't remember which one does the arrow. Is it this one?
Mm-hmm.
Oh, here's my arrow. Yay! You can see in the denominator there is a variable. So this brings across the issue of a domain in which it's not all real numbers. The domain is not all real numbers because we cannot in mathematics divide by what number, Matt?
0.
We can't divide by 0. So according to this rational expression, x minus 1 cannot be 0. And when you solve for that by adding 1 to both sides, you're going to get x cannot be equal to 1. So the domain is going to be all real numbers except x equals 1. Very good?
Mm-hmm.
All right. So that's a rational function. Now, I think I've run out of room on this screen. It kind of looks like a chalkboard. I like it. Next. So with rational functions, which you may notice when you graph them, is like the one I just had, I think the domain, it couldn't be 1, right?
Mm-hmm.
So at 1, in that case, there would be what we call an asymptote. And so the function, I'm not graphing that function in particular, but might look something like that or that. But it basically has a vertical asymptote somewhere where the domain cannot be that value. Does that make sense? I don't know if that makes sense. We're not going to graph them all that much. We're going to let you do that in Math 80. But that's what is going to go on with those domain problems. Moving on. And now the very last functions that we will analyze are those that are radical functions. And I believe radical functions, the ones that we're going to look at is, it's going to be like the square root of some, again, some polynomial. P is a polynomial. I'm trying to think of a case where maybe, I mean, it could be a rational, but those will be an 80 too. But the basic thing with a radical is you're going to have a variable in the radical. So, an example would be where you have the square root of x, what,
Plus
minus
2.
5? Oh, you went positive, I went negative. So the square root of x minus 5, for this expression, now the thing with square roots, when we're going to mainly be looking at square root functions, and I'll let you go over all the other roots in 80, but in square root functions, inside that radical must be, oh, let me use my little pointers, inside the radical here, we must have a positive value because we don't know the square root of a negative number is not real in our world. Next semester in Math 80, you'll get to talk about that. So x minus 5 is got to be greater than. Now, can it be equal to 0? Yes, because can we take the square root of 0?
Sure.
Sure. The square root of 0 is 0. So in this case, x minus 5 has to be bigger than or equal to 0. So that means, I add 5 to both sides, I get x is greater than or equal to 5. So my domain in this case is going to be, should I do it in interval notation or just the set builder?
Why not both?
Because I'm running out of room. There we go. So there's our domain, is x has to be bigger than or equal to 5. There was something else that I wanted to talk about. Oh, so let's take a look at some of these. Moving on. Oh, before we take a look at them, just remember that with radical and rational functions, you have some issues with the domain, values that we can't input into the function and get a real value out. Okay, Matt made the comment about rational and radicals. Oh, domain, having a domain error means you have to check your solutions.
Oh, yeah.
Okay, you did. So just wanted to put that in. But now we're going to have a little test of skills. And I'm going to write some examples and ask you what kind of equation. And classify the equation as either linear, quadratic, radical, or rational. Here we go. Don't be fooled.
So the specific thing.
Oh, what?
The specific thing.
Yeah, be as specific as possible. So how about this equation? Take a look at it, pause if you need to, and identify what type of equation is it. And Matt here says he knows the answer, so I'm going to call on him. Go ahead, Matt. How would you classify this one?
Linear.
Linear! And it is linear. It's an ugly kind of line, but that's okay. It's fun. A lot of people would look at that radical 5, square root of 5, and say, this is a radical equation. But remember, to be a radical equation, you have to have a variable inside the radical. And there ain't no variable inside that radical 5. So there's an x, and the x is to the first power. So that's why we classify this as linear. Any questions?
We really like that new arrow, don't you?
I love the new arrow. Okay, how about this one? What am I going to do? 3x times x minus 2 is equal to 3 x again. How's that? How would you classify that one? Think about it. Pause if you need to. I'm going to go to one of my favorite mathematicians over here, Matt. Matt the mathematician, what's the answer?
Quadratic.
Ah, yes, this is quadratic. Very good. He is 2 for 2, and I hope you are as well. But if you're not, that's okay, because it only matters when you take the exam. This is just a fun game. So how to get it was quadratic? Well, in order to identify the equation, you've got to simplify both sides. And when you multiply the 3x times x, you're going to get you're going to get 3x squared. The rest doesn't matter because we know 3x times 2 would be x to the first, and so on. So we've got a quadratic equation. You would solve this by setting it equal to 0. How about this one? 4 over 3x plus 2 is equal to 7. What type of equation is that? Pause if you need to. And Matt, give us the answer.
Rational.
Rational. And what made you say it was rational?
It's a ratio.
It's a ratio, but there could be a ratio and it still be linear. There is a variable in the denominator. Yes, see the x in the denominator? X in the denominator. And so remember, this also means that there are certain values of x that we can't have. There's a domain issue here. X cannot be, in this case, and see if you can work it out for yourself and get that x cannot be negative 2/3. I hope that's right. Is that right, Matt?
Mm-hmm.
Cool. Nice. Hey, want to do more? Sure. Let's do another one. Okay, how about this one? Again, what kind of equation? What is this? A, B, C, D? This is D. 2 minus x is equal to the square root of x minus 7. Dun, dun, dun. What kind of equation is that? Matt.
A radical equation.
Radical equation. Why is it radical?
Because it's super cool.
No, that is a lame math joke. No lame math jokes. Matt says it's
Coming
radical
from you?
because there's a variable in the radical. You
Yeah,
look
that's what I
inside
said.
the radical and there's a variable. So life is good. So you will have certain steps for solving this radical equation. And remember also, because there's a variable in the denominator, there's also a domain in the denominator, there's a variable in the radical. There's also a domain problem. And we know that x would have to be bigger than or equal to 7. And you, again, work on that. Make sure you can get that. Last one that I'm going to give you. How about this equation? How would you classify that one? Don't get fooled. Don't get fooled. Matt? What is the best classification? The best classification for this is a linear equation because, again, even though there are denominators, look, what is in the denominators? Constants. 5 and 2's are in the denominators. There are no variables in there. So we've got an x to the first power. This is old school. We can solve this equation just by using our inverse operations. Cool. So x over 5 is equal to, that's going to be a 4, right? 7 halves. Multiply both sides by 5, and x will be equal to, ooh, that's a crazy 35, but that'll work, 35 halves. But we can solve that very nicely and get our x, and if we were to graph that function, we would have a line. So enjoy this. This is your short review of Math 60 online in a nutshell. I'm going to sleep now. You have a good night.